Good morning. Today we're going to talk about how two variables are related in chapter 4. And so far this semester, we've only discussed one variable at a time, whether it was quantitative or qualitative. But now these two variables could have a relationship or no relationship at all. And we want to find out what indicators, what measurements can we use to decide if there is a relationship and how strong that relationship may be. The first variable is going to be called the response variable. And in algebra terms, we always call that the dependent variable. This variable is usually called the y variable. And the other variable is called the explanatory variable, which in algebra terms, we call that the independent variable. And that's usually called the x variable. And so you can turn into your course pack to page 107. We will start looking at this information. So there's our response variable, aka the dependent variable, or y. It's a particular focus of a question in a study or experiment. It's what you're trying to find out. This variable is usually represented by y. And the explanatory variable, aka the independent variable, is any factor that can explain variations in the response variable. In an experiment, it is manipulated by the researcher. This variable is usually associated with the letter X. So please read through example 1 here. And in a moment, we're going to describe what we think the explanatory variable is in the response variable. Now that you've had a moment to read through this, we want to find out what is the explanatory variable that neurologists are researching. And that would be the time to walk. The 50 meters. What is the response variable? What are they trying to measure? And they are trying to measure the psychometric score to let them know about the cognitive decline. That's what they want to know. So they're going to measure the psychometric score right here. Explain your choices for part A. So researchers believe that the time to walk the 50 meters may explain the cause of the cognitive decline based on the psychometric score. And going back to what we learned in lesson 1.1 and 1.2, would this be an observational study or designed experiment? So this would be an observational study. And that's because there's no treatment given. And we did not randomly assign them to groups. Assign the subjects to groups. Okay. We're not going to look at a scattergram and what a scattergram tells us about visually about how these two variables could be related. So a scattergram can also be called a scatter plot. It's a graph that shows the relationship between two quantitative variables measured on the same individual. The explanatory variable is graphed on the horizontal axis. Okay. And we say AKA, that's the X variable. So it's at the bottom of the graph. And you'll want to go back and use this as reference while you're working on this entire chapter, because it's kind of takes a while to get to know. The response variable is graphed on the vertical axis, AKA that's the Y, and that is on the left side of the graph. So this first set of data I'd like you to get familiar with is the in 1962, they took and collected data on 201 countries all around the world, and they collected the fertility rate of the women, so the number of births per woman in those countries. And because they're averaged, they can be decimals because the average birth per woman for women. And then it's also the life expectancy in years for women in those countries, the average life expectancy. And again, because these are both averages, they're quantitative values. When we would have collected them, they would be discrete. I either had 2 births or I gave 3 births, but because it's an average for the country, it's going to be considered a continuous variable. So go ahead and get familiar with this data and then flip to the next page. So on page 109, it says, what does each dot represent? So each dot on this graph on page 108 represents a country. What is the explanatory variable? That is the fertility rate. And what is the response variable? That is the life expectancy. So let's write down the graph. So the fertility rate, what is on the bottom here is always the explanatory variable. And then this is the horizontal, the life expectancy is always the response variable. What type of data is the variable fertility rate? So I already mentioned that they're both considered quantitative continuous because they've been averaged. Interpret the meaning of the US's values in 1962. So we're going to go back to the table. Notice in the table, this is important too you'll notice this sometimes in the chapter review worksheets that you're working on. There's this ... And what that tells us is that there's data in between here we can't see, and you don't need it because I'm going to give you everything that you need. So always notice when you see ... there, everything you need is probably in another table of summary statistics, but this is just letting you know that the data started with Afghanistan. You can see this goes in alphabetical order, ends with Zimbabwe, and there's the data for the US, which is 3.48 births per woman and 70.3 years of life expectancy. So we're going to describe this as in 1962, the US had an average of 3.48 births per woman and a life expectancy of 70.3 years, and that's for women. In 1962, the African country of Rwanda had a birth rate of 8.2 births per woman and a life expectancy of 45 years. Circle and label Rwanda on the graph. So 8.2 births, 8.2 is going to be just past that. So it's either one of these, but 45 is their average life expectancy. So that would be right here is Rwanda. Being able to read the graph is very important in being successful. What relationship do we see between the variables? So it looks like the more births per woman in a country as an average, it looks like their life expectancy is lower. And it looks like the countries here that had fewer births per woman, their women had a higher life expectancy. So those countries with a higher fertility rate seem to have a lower life expectancy. Now, does that necessarily mean that having more children causes you to not live as long? No. Some might say yes, jokingly, right? Like kids cause us stress, but that's not necessarily true because this cannot be considered, remember, this cannot be considered a designed experiment because we did not give anybody a treatment. We did not tell them to have kids or not have kids, and we did not randomly put them in groups. We just collected data and looked at the situation. Okay, so in 1962 was the year that the terms first world and third world were coined. Explain how the graph reveals the differences between these two groups. So a first world country would probably be in this area. Okay, first world countries would have better health care. Sufficient food, housing, things like that for their citizens of their country. So third world countries is all the opposite. Terrible health care, poor living conditions, contaminated water, and you can see that too in the graph. The third world countries would be these countries over here. Okay, so if we turn to page 110, we're going to see some graphs. So far, we've only talked about how we can see that data or two variables are related to each other visually on a graph, right? And we want to kind of put that together, like what do typical relationships look like here graphically? And so we can see that there are two typical relationships. One is a positive linear relationship, is what we're going to call this, meaning that it kind of looks like it's going in a line. And remember, real life data doesn't happen in a perfect line. This would be some kind of a positive relationship. Okay, so as your x variable goes up, the y variable also goes up. Or it might be this negative relationship, okay, which is also called an inverse relationship. as the x variable goes up, the y variable goes down. Okay. So we're only going to focus on linear relationships in our class this semester. If you take a normal algebra class, they're going to focus on other ones, which you might have already seen. This one's called a quadratic. This one's called an exponential. And there's other quadratics that you could look at. They kind of go this way. There's other exponentials that go this way. However, again, we're only going to focus on the linear relationships, a direct relationship or an inverse. And then sometimes down here, you might see this down here at the bottom left. There's absolutely no correlation. Okay, sometimes you do graph data values from two variables and realize there's really nothing, there's nothing going on there. Okay, so how do we decide how strong the relationship is or the direction? And so if you turn to page 111, when we talk about a linear relationship, we talk about two things. One is the direction, whether it's a positive or negative relationship. And then we also talk about the strength of the relationship. So the strength of the relationship could be perfect, strong, moderate, or weak. And we want to identify the two characteristics for each of these 6 variables. So this one, we would say that this is a negative. And we would say that this one is, I would say this one is a perfect relationship. It looks like it's a perfect straight line. And the same thing over here. This one is definitely a perfect. But this one is a positive. Okay. This one on the middle left, I would say that that's a strong. It looks like it's very, they're very much gathered together in the center. And this would be a strong negative. This next one, I would say it's in between strong and moderate. We'll call it a moderate. And this is a positive. And the bottom left, I would say these are both weak. The one on the right looks most like there's some kind of a positive, but it's definitely weak. I would say this one's none, but you could maybe say there's some kind of a negative thing going on here. And so after looking at this page, you're probably thinking, how am I ever going to be able to make these decisions? Because, what Mrs. Main might think is matter or strong or weak might not be what you're thinking is matter or strong or weak. So can we all agree that we need some kind of a numerical measure to help us decide how strong or weak these relationships are? And yes, I would agree. We do need some measure. And that measure is right here for us. It's called the correlation coefficient. Everything in these gray boxes is very important. You need to have some notes about them on your note sheet for the midterm. There's some good information on your yellow gold sheets about the correlation coefficient here. So on this one, this is the correlation coefficient. And so it's already on your yellow sheet. Remember, that's the R. The R squared we're going to talk about in lesson 4.3. So don't worry, we're getting there. Okay, the correlation coefficient R. And they show it as a little r, but it's actually always shown as a big R for some reason in StatCrunch and under TI 84. We're never going to have to calculate this. This is just showing you how it's calculated. But R is a numerical measure that's going to tell us that direction and the strength. So we don't have to worry about just looking at the picture and making a decision. Again, we're never going to have to calculate this. It's not resistant to outliers. So if you have outliers, it's definitely going to affect that R and make it look like there maybe isn't a very good strength between the relationship of the variables. R is unitless. We usually round to 3 or 4 decimal places. R does not tell you if a relationship is linear. However, if you already know the relationship is linear, R can tell you how strong the relationship is. Okay. So some properties of the correlation coefficient. A positive means that as x increases, y also increases. That's the direct relationship we talked about. If r is negative, it means that x increases and y decreases. They go in opposite directions. And if you take the absolute value of r, not looking at positive or negative, but the absolute value of r, it tells you the strength, okay? And so you can see at the bottom of the page on 112, out here, if you're the absolute value of r, where it's closer to 1, so a -1 out here or a +1, that's a perfect negative or a perfect positive. And we can also see that here where we spelled out the inequalities. So the inequalities here, if you rather read an inequality where a number is between two values, it will give you the direction and the strength, or you can just use this number line, okay, where 0 is right here in the middle. So you can see here in this red area that between a -0.3 and 0.3, there's no linear relationship, okay, and that is right here in the inequalities. And then if you move out from there, between the -0.3 and -0.5 and +0.3 and +0.5, then we have our weak relationships, negative and positive. And then we move out to the next space in blue, where we have the moderate positive and moderate negative. And then ideally where we want to be is either 0.8 to 1 or -0.8 to a -1. And that's where we have our strong positive or strong negative relationships. Again, these are on your yellow gold sheets, which I encourage you to pull out from your course pack right away and get those stapled together because we're going to be using them all throughout the semester. Okay, so let's go ahead and flip the page. Page 113 gives us an opportunity to look at some scattergrams and just kind of put an idea to it, how we interpret these correlation coefficient values. I'd like you to pause the recording and do your best guess effort to take these values here. Notice there's 1, 2, 3, 4, 5, 6, 7, 8 of them. So there's one for each of these 8 graphs. Do your best guess at what you think matches the graph with the correlation coefficient. When we come back, we'll put them together. Okay. Okay, so hopefully you've done your best guess effort here. And I would say the first two I would start with are the ones that I know are the perfect positive and perfect negative. So this is the perfect positive. And this one is the perfect negative. Okay. And then we have, then I'm going to the ones that there's not really a relationship because I think those are easy to decide too. The 0.11 is positive, but it's not good. It's very weak. And so I would say that that's this one down here. The dots are pretty spread out. So I'd say that's the 0.11. And then the -0.22 is something similar where the data points don't fit well at all, but there's some kind of a negative relationship. And usually the ones that are the weak are where the line's very flat. Notice on the negative one, it's definitely going up and down, and the same with the positive one. The ones that are weaker, the linear line is pretty flat. And so I would say this right-hand side one right here is going to be the -0.22. Then as far as the strong relationships, we have a -0.95. And I would say we know that this one's clearly pretty strong and it's negative. So this is our -0.95 here. And our 0.83, this is pretty strong as well. Not as strong as the one to the right, but it's pretty strong and it's positive. And then we have the last two left here. One is definitely positive, one's negative. So we know this one has to be the 0.59 because it's positive. And that would be a definite moderate. And this is the -0.44. So let's see how we can put these in context of a real life situation here. So on page 114 in your course pack, we have a data set here that we're going to work with in the next, all of chapter 4, 4.1, 4.2, 4.3. We're going to see that we bring it back. It's the table shows the percent of students who receive free or reduced price lunches compared with the percent who passed the math portion of the state exam at public schools in Sandusky, Ohio. So in StatCrunch, I've already put this data in. You can find it in our class, or you can search for it in StatCrunch in general ones, but look for the one in ours. Let's answer these questions first, and then we'll go there together. So it says, what is the sample size? So if you count the rows here, there are 13 data points. What is the explanatory variable? And that is the variable that we think gives some explanation to the response variable. So the explanatory variable is the percent on free reduced lunch. And what is the response variable? That's the percent passing math. So they think there might be some relationship between the students that are on a free or reduced lunch and they're passing math. It's interesting. So let's go ahead and go to our StatCrunch. And in our class, it's called CP 4.1 free lunch for course pack 4.1. So here we are, and it says compute the correlation coefficient. So to do that, we're going to stat, okay, and we're going down to regression in simple linear. Stat, regression in simple linear. And then we're going to put in our X variable. That is our var1. And that is our percent free lunch. And then our Y variable is our percent passing math. Okay, so percent free lunch, percent passing math. And then we are going to leave the where optional, the group by optional. We're not doing any hypothesis tests. We can leave all that there. We just want to go ahead and look at the model estimates, the residuals, and everything. It's going to give us everything that we need here. So go ahead and hit compute. And this is what it looks like. And it's going to look very overwhelming. So notice that it gives us a whole bunch of stuff that, and we're going to bring this all up later in 4.2. So don't worry. But right now we just want to verify here the sample size is 13. You do want to notice this right here where it says percent passing math equals. This is our equation, and you've probably done linear equations before in an algebra class where it was y equals mx plus b, and we're going to talk about that in lesson 4.2 just for chapter 4. But this is our y equals mx plus b, except for notice we said that we're going to call y percent passing math. So they wrote the words percent passing math, which I think is great because that's how we remember it, right? And we called x percent on the free lunch, and so right here they called x percent free lunch. So here is our y equals, and here's our mx. So they do, there's opposite, but here's our mx, our m, our slope is a negative 0.28, and then there's our x, and then our b, which is our y-intercept. Again, we're going to talk about these in 4.2, but it's a great time to bring them up. Right there they are. So you're definitely going to always want this row right here. The correlation coefficient that we're talking about in this lesson 4.1 is right here. It's negative 0.6878, and we're going to round that to a negative 0.6879. Okay. And what's cool is they also give us the y-intercept and the slope right down here. So if you look, when we get to our linear equation, they say intercept, here's our estimate for the intercept, and slope, here's our estimate for the slope. So we'll worry about those later. Okay, and we could have looked at some graphs if we wanted to as well, just to see what this looks like. So we could go down to scatter plot, and again, choose our percent free lunch and our percent passing math. And you can also go down here and click on an order of 1 overlay polynomial and just click on best fit. And then I think that's all we want to do. So yep, so go to graph and scatter plot and your x variable, y variable, and then choose this to overlay polynomial order 1 with the best fit and hit compute. And they did put the line right on there. And notice I'm hovering over it and it gives us that the y equals mx plus b, but it gives us y equals b plus mx. So if you just kind of hover over it, it gives it to you right there. And in our edit, we could probably get it to overlay, not the equation that we want. Add to hover info, no, display line. Let's say display line and see if, oh, no, we don't want to do that. Let's edit that back out. Okay, there we go. So again, if we hover over, we can get our equation in a scatter plot. Okay, so let's go back to our page that we're commenting together here. So everybody wrote down their correlation coefficient, -0.6879. And then E says, comment on the type of relationship there appears to be between percent of children on free and reduced lunch and their math scores. So if we go to our yellow sheet and look at our inequality and find out where -0.6879 is, it's in here, right? It's in the moderate negative. So we're going to write moderate negative. You're going to do the same things for your project for chapter 3. Explain why this is an observational study, not an experiment. Well, we can't force people to be on free lunch, right? Can't force children to be on free lunch, i.e. no treatment. Okay. Explain why it is not possible to argue that a higher percentage of free and reduced lunch causes lower exam scores. And that's because what we said up here, whenever we talked about in 1.2, correlation does not mean causation. So if you do not have an experiment, then you don't have causation. So observational study means that you've only got, so you could have correlation, there's some kind of relationship, but it doesn't mean causation. That's the critical piece. And the last but not least, we always bring up here in 4.1, what I just said, correlation is not causation. Because there's lurking variables that affect both X and Y. Okay, so in our comment over here with this, the children on the free and reduced lunch, we can't say that being on free lunch causes you to not pass math. What we can say is being on free lunch might indicate that you come from a lower income family that maybe doesn't have resources for extra tutoring. Quite possibly they're single parents, single mothers. If not, they're both working, both parents are probably working 2 jobs. They don't have extra time to spend with their children at home, helping them maybe with their education. And so there's lots of other things that are kind of lurking in the background. We call those lurking variables. Okay. So this last one is kind of an example, this joke here. It says in the cartoon, it says statistics show that crime rates rise with the sale of ice cream. Now do your part and move along. So, the cartoon is depicting that there is a strong positive relationship, right, between crime rates and ice cream, which is true. If as crime goes up, crime goes up and ice cream sales goes up too. It's kind of weird. It doesn't mean that crime causes ice cream sales or that ice cream sales causes crime. Okay. It means that in the summer, there's heat, right? It's warm outside. And in cities where it's warm, or seasons where it's warm, crime goes up. It's just there is a relationship there. And also in cities where the weather is warmer in the summer, right? When the heat goes up, ice cream sales go up. So that is the relationship we're talking about. And we're not going to look at this one. But what we're saying here is that it's important to recognize, essentially this one down here below, is that just because a student is on free and reduced lunch does not mean that they're not going to pass math. It means there's a relationship between the two, and we want to kind of further that relationship and try to see what else is going on. So that ends 4.1. Please come back and enjoy 4.2 and 4.3 and adding on to what we've been learning in StatCrunch together. See you soon.